All right. So, welcome to the session. This is section 10.2.1. How can I find the measurement? And we're talking about indirect measurement. When most people think of measurement, they think of using a ruler or tape measure to find a length. However, during this course, you found the measures of objects using other types of information, a process called indirect measurement. Today's activity will provide you with opportunities to connect several ways you know for finding measures. As you work with your team, ask the following questions. How can I visualize it? What information do I need? And which strategy should we use? Now, I will tell you that I think this is probably one of the most important things you can do is how can you visualize it? Can you draw it? Because drawing it has a big influence on problem solving, and it lets your brain relax while you're drawing it, and it kind of creates, it gives you time to think about how you're going to solve the problem while you're drawing what's going on in the problem. So these are very visual problems that we're going to be working on the next few days. So to kind of give you an idea of what I mean by drawing a good drawing, here is a demonstration of drawing a quality diagram. Charles was standing on the 0-yard line of a football field flying a kite. The kite was flying directly above the 0-yard line on the other end zone. His 500 feet of kite string was stretched tight because it was a windy day. How high was his kite flying if he was holding the string 4 feet above the ground? So we could get all crazy and we could make like a 3D football field where here's one end zone, that's the 0-yard line, and here's the other end zone, and this is the 50-yard line here, right? And we know that he's flying a kite that is, so let's say he's standing here and he's got a kite on a string that's up over here, and it is exactly 500 feet above the 0-yard line. Well, we could draw that, or sorry, I have that wrong. I've got it backwards. His kite string is 500 feet, and it's stretched tight. And they want to know how high above the ground he is. Well, when you start drawing in 3 dimensions, it gets a little bit difficult to start seeing some of the mathematics that's going on. So let's just look at it from a side view. I think a better drawing might be something like this. So we start off, we say this is going to be the 0-yard line here, and the other 0-yard line is down here. And maybe we'll have our guy standing right here, our person, what's his name, Charles. And Charles has a kite string, and nothing has to really be drawn to scale, but we do want this kite to be over the other 0-yard line. And our job is to figure out the altitude or the height of that kite. Now, we do know that he has a 500-foot kite string, and it is stretched tight. That's kind of an important phrase right here because it's telling me that this is a straight line. And I want to know how high above the ground that is. Now, they do tell us that he's holding that string 4 feet above the ground. So if I were to put a number right here, this part is 4 feet above the ground. Now, as I'm looking at this problem, trying to figure out how high this is, the picture I've drawn looks more like a trapezoid, and we haven't really done very much with trapezoids. We have done stuff, though, with triangles. And what I can do, and I'm talking about a diagonal length here, and whenever I think about diagonal lengths, my first thought is the Pythagorean theorem. And you know the Pythagorean theorem. It says legs squared plus legs squared equals hypotenuse squared. So if I could call this diagonal my hypotenuse, then I'm looking for 2 legs, but I need a triangle first. So I think what I'm going to do is I'm going to cut straight across here, 4 feet above the ground. I'm going to call this 4 feet, and we'll call this L for leg. And then this distance here is the distance between the 0-yard line and the 0-yard line on a football field. Well, a football field is 100 yards long. So in feet, that would be a 300-foot length. So this leg is 300 feet. This leg is L. And this hypotenuse, I'll make it a capital H, that hypotenuse is the 500. So if I would like to find the length of this segment from here to here, I could say L squared plus 300 squared equals 500 squared. L squared plus, let's see, that's a 9 with 4 zeros, is equal to 25 with 4 zeros, so 250,000. If you subtract the 90,000, L squared is going to equal 160,000. So L is going to be the square root of that, or L will be 400 feet. So this is 400 feet. But when I ask you how high was his kite flying, we have to remember that the height of 400 is taken from 4 feet above the ground. So his kite is 404 feet high. And that would be the answer. So a good drawing really helps us in a problem like this. That means you might have to read the problem a bunch of times to figure out what the drawing is going to look like. And so read it, draw it, spend some time with the problem before you start attacking the problem. And then once you get that going, it should be easier to solve the problem. So the next problem we're going to do then is problem 1081. The beautiful young princess of Polygonia is very sad. A mean ogre has locked her in a tower of a castle. She could escape through the window, but it's 50 feet above the ground, a long distance to jump. A moat full of alligators surrounds the tower. Naturally, Prince Charming wants to rescue her. The prince has some rope. His plan is to use an arrow to shoot one end of the rope up to her window. The princess can then slide down the rope to the other side of the moat, and off they will ride into the sunset. Help the prince save the princess. Draw a good diagram of what we know so far. So some of the things that your diagram should have is it should have a tower. There's a window 50 feet above the ground because that's where she is. She's stuck in that tower. There's going to be a moat around the tower and alligators. And then there's a prince, and the prince has a rope. His plan is to use an arrow to shoot one end of the rope up to her window. So he's going to shoot one end of the rope to the window. The princess can then slide down the rope. So I assume the rope's not hanging straight down, but maybe it's going to be hanging at a diagonal down to where the prince is. And off they will ride into the sunset. Okay, so let's see here. A good drawing. We need a good drawing of this. So I'm going to do a little bit of work right here just for a moment. Okay, so we need to do a little bit of drawing on this problem here. So I know that I've got there's going to be some water because there has to be a moat. And I know that I need to have a tower. So I'm going to put this tower right sitting in here. And I'm going to bring that all down to the very bottom for right now. That tower is going to have a window for the princess to be stuck up in. In my tower, I need my drawbridge. And then we're gonna put a lid on top of that tower so that it looks about right. How about that? That looks pretty good. We do need a princess. So I'm gonna stick Princess, what was her name? The Princess of Polygonia. I'll stick her up in a tower. And we need some alligators because, you know, it said there were alligators in this moat. Yeah, I'll put the little guy right here. That one there. And we need a prince because the prince is going to. So this is my prince, and the prince is going to come and save that the damsel in distress, as we might say. And maybe we should put some like reeds, or let's see, something little, you know, at the edge of the thing. There's got to be some little tufts of grass. And then we're going to put a let's put a seagull, because you need some birds. Maybe the sun's going to be over here, because, you know, got to have some sunlight, right? All right, so here's my picture. And I know that this prince is going to be using a rope. And he wants to take that rope and he wants to shoot the rope up to the window and tie it down here so that the princess can slide down the rope. So if that's the case, then we're going to need a rope. And I think what we'll do is let's make sure that rope is nice and tight so that when she slides down. Now, do we want the rope up here at his head? I think he's going to probably hook that down here. But until we know for sure, we'll just leave that right there. So this is going to be my picture. And that picture is then going to be used throughout this problem here. So let's kind of continue on, and we'll come back to this picture and solve some problems. Let's see here. Help the prince save the princess by answering these questions. A, the prince knows that the closer he is to the tower, the less rope he will need. However, he's not sure how wide the moat is around the castle. In a book about the castle, the prince found a diagram of the tower and the moat. Using his ruler, he found that the window in the diagram is 7.5 inches above the moat, while the farthest edge of the moat is 1.5 inches from the base of the tower. How close to the tower can the prince get? Draw a diagram to show your work. So the diagram of the map. So remember here, as you're reading through this, it says right here, in a book about the castle, the prince found a diagram. Using his ruler, he found that the window, so this was where the window is for the princess's window. The window's right up there. He figured out that the window was 7.5 inches above the ground in the drawing, and that the moat was 1.5 inches if he could come right to the edge of the moat. So if we were to look at that on our picture here, so for part A, first of all, you need to have this drawing, so pause your video if you don't have a drawing. For part A, I want you to add their little side drawing here, which basically says that if this is the rope, that this is 7.5 inches, and this was 1.5 inches. And we know in the Princess Tower that her tower is 50 feet above the ground, above the water. So we can look at this and we can see that the 7.5 corresponds to the 50 inches. And the 1.5 would correspond to the moat. So if you look right in here, can you see that there's going to be a right triangle right here, right? So I can draw that in to help you out. If you come straight down here and straight across the water, you get a right triangle. And this 50 is a leg of that right triangle, and the distance across the water is the other leg, and this is my rope. So keeping those two pieces in mind, let's first, for part A, use a proportion to solve for the missing distance across the water. 50 is to 7.5. So 7.5 is to 50. Let's do it this way. As 1.5 is to, and then we'll call that the distance across there. So let's call it X. So I'm looking for the distance right across there. You could cross multiply this. You could figure out the giant one that's going to get you from 1.5 to 7.5. Most people would probably cross multiply. So 7.5x is equal to 50 times 1.5 would be 75. When you divide by 7.5, x is equal to 10 feet. We now know the distance across the moat, and we can add that distance to our picture. So I'm going to say that the distance across this moat, this leg that we have here, this is going to be 10 feet. So we're going to need to know that throughout the rest of this problem. Problem B, before he shoots the arrow, the prince wants to make sure he has enough rope. If he needs an extra 2 feet of rope for tying it to the window frame and holding it up on the ground, how long does the rope need to be? All right, so let's see. We are now asking the question about the length of this diagonal rope. Anytime we have a diagonal, we should be using the Pythagorean theorem. So for part B, we're going to say 50 squared plus 10 squared equals hypotenuse squared. This is my H, my hypotenuse. 50 times 50 is 2,500 plus 10 times 10 is 100 is equal to H squared. When you combine those, you get 2,600 equals H squared. To unsquare something, we need to take the square root. So the square root of 2,600 is going to be the length of the rope before we add the extra the extra lengths for pinning it to the window and the ground. So let's see, 2,600 square rooted, so I have to take the second function. See, there's my square root. Is going to be 50.99 feet. So let's call that 51 feet. So he has 51 feet exactly, but he still needs a little tail end to tie on the ground and to tie up here. It says he needs an extra 2 feet. So he needs 53 feet of rope. Now, so far, everything we've been working on is either a proportion or going to be Pythagorean theorem because we're creating right triangles. Anytime we have something that has a vertical component, a horizontal component, and a diagonal piece, we're probably looking at the Pythagorean theorem for calculating the length of that diagonal. All right, moving on. Let's see what we got. Part C, the princess thinks she might fall off the rope if the slope is steeper than 5/4. The prince plans to attach the rope to the ground at the edge of the moat, and the princess will attach the rope to the window frame 50 feet above the ground. Let me read that again. The prince plans to attach the rope to the ground at the edge of the moat, and the princess will attach it at the rope to the window frame 50 feet above the ground. Basically what our picture shows. Part I, according to the prince's plan, what would the slope of the rope be, and would it be too steep? All right, so this is now part CI. They want to know if this is the picture, what is the slope of this rope? So part C, we will do that here in red. All right, part C, if I can get it to right. Letter I, the slope. The slope of this line, if I do rise over run, is going to be a 50 to 10 slope. Now, is this slope positive or negative? Well, it looks negative if you're looking at it from our side, but if you were looking at it from the other side, it would look positive. So in reality, we don't care about the sign of this slope. What we care about is its magnitude, how steep it is. So I'm going to think of it as the absolute value and not worry about the sign. 50 over 10, that's going to be a 5 to 1 slope. And it said in order to be safe, let's go back here, the princess thinks she might fall off the rope if it is steeper than 5/4. Would it be too steep? That's the second part of the question. So let's see. How does 5 over 1 compare to 5 over 4? Well, let's see. This is like 1.25, 1.25, and this is 5. This is greater. So the slope of this line is bigger than the slope that's safe. So I would say it's too steep. Problem D. If one end of the rope is attached to the window frame and the prince holds the other end of the rope 2 feet above the ground, where would the prince need to stand? Oh, I'm sorry, I forgot part 2. Part 2, should the princess worry about the prince's plan? How steep would the prince's rope be? Find the angle of the rope. Find the angle the rope would make with the ground. Use a protractor to measure that angle. So since we didn't do it to scale, we won't be able to measure that angle, but we can answer the question, should the princess be worried? Yes, she should. If we were going to measure that angle, we could get some graph paper here, and we could say, okay, if we were to insert a grid, and we were to do, let me insert a grid right here, visible but bigger. And we were to have a vertical line that goes 5 boxes. Every box will equal 10. And a horizontal line that goes 1 box, that would equal 10 feet. And the diagonal line that would go like this, then we could actually use a protractor. Oh, not a compass. Grab the wrong one. Let's do a protractor. We could use a protractor to measure this angle here. So if I measure that angle, put the vertex of the angle here, here's 0, 10, 20, 30, 40, 50, 60, 70. Here's 80, that looks like 78, 79. So maybe somewhere around 78 degrees. We could say that this is 78 degrees approximately, if that's a right angle. So to get the angle of this by measuring with a protractor, it's approximately 78 degrees, and that is too steep. Okay, now on to part D. If one end of the rope is attached to the window frame and the prince holds the other end 2 feet above the ground, where would the prince need to stand so that the slope of the rope is only 5 over 4? If he has a rope that's 62 feet long, will his rope be long enough? Justify your conclusion. Draw a picture and label it. So now we're going to have to draw a new diagram so that we can have this rope 2 feet above the ground. This one is it's more closely associated with the kite problem we did earlier, where he was holding the kite above the ground. So I'm going to say here, whoop, I need my pen back. Let's say that this is my tower, And this is the moat. And he's going to hold that rope. So she's going to attach it here 50 feet above the ground. And he's going to be holding that rope 2 feet above the ground. Right to here. Okay. And we want to know how far back would he have to stand? How far does he have to move backwards from the tower, total distance, so that the slope of this rope, we want a slope of 5/4. Okay, so from top to bottom is 50 feet. If I were to go straight across, we can get the slope if we know the rise and the run. Now, if I know that this is 2 feet, then from here to here must be 48 feet. So I'm going to erase the 50 for a second, and I'm going to call this 48 feet. 48 plus 2 is the 50. I want the slope of this line, and this is my unknown because they asked me how far back does he have to stand. So I'm going to call this, we'll call this X. That'll be fine. So 48 over X, remember this is part D, by the way. 48 over X has to equal 5/4. If I were to cross multiply this, 5x is going to equal 192, because 4 times 48 is 192. Let me just double check that. I did that in my head pretty quickly. Yep. Okay. And so now when I get my giant 1 and I divide by 5, x is going to equal, what's that? 3, remainder 42, 6, 36.4 feet. So if he stands back 36.4 feet, that ratio will be exactly 5/4. And I'm going to just double check that number. 192 divided by 5. Yeah. 38 point, let's see, 38. So 342, 8.4. There we go. So now I wasn't feeling good about that number. But they ask us, how long does is that rope, is he going to have enough rope if he only has 62 feet? So if I know that this now is 38.4, how long is this rope going to have to be? So we're back to that hypotenuse problem. So let's see here. 48 squared plus 38.4 squared has to equal hypotenuse squared. Now I will use my calculator. 48 squared, 2,304 plus 38.4 squared, 1,474 I just lost it, 56 equals h squared. Add the two numbers together. 3778.56 equals h squared. So h will be the square root of that number. My square root is a second function, so take that second. Now I can take the second root right here, and I get 61.47. 61.47. So h is 61.47 feet. But wait, he needs an extra 2 feet because he needs 1 extra foot here and 1 extra foot here to tie the two pieces off. So he needs 63.47 feet. His 62-foot rope is too small. So this diagram led us to do slope and Pythagorean theorem. So far, this has been a really good problem. Let's see what question E holds for us. So, question E, what if the prince holds his end of the rope 5 feet above the ground? Can he stand in some location so that the rope is not steeper than 5/4? The rope is still 62 feet long. Justify your conclusion. So, where can he stand so that the rope is not steeper than 5/4 if he's holding it 5 feet above the ground? Okay, new diagram. So he's standing back here somewhere, 5 feet above the ground. Looks like the same drawing we did before, only bigger. If this is going to be our 50-foot distance to the window, but this already is 5 feet, then this part has to be 45 feet. What if the prince holds his end 5 feet above the ground? Can he stand in some location so that the rope is not steeper than 5/4? So how far does that have to be so that 62 feet will work? So let's see here. 62 feet, but one of those feet is to tie on that end and the other foot is to tie on that end. So he really only has 60 feet. That's how I interpret it. And I want to know how long this has to be. If this is 60 feet and this is 45, what is this distance? And is that distance going to be enough so that it's not steeper than 5/4? So let's go back and do the Pythagorean theorem again. In this case, the x is a leg and the 60 is the hypotenuse. So we could say x squared plus 45 squared equals 60 squared. X squared plus, I think that's 2025 equals 3,600. I am going to double check my math. 45 squared, yep. So when I subtract the 2025, x squared is going to be equal to, let's see, 5, 10, 9, 10, 5, 7, 5, 1,575. So x is the square root of that number. So x, I'm going to double check that too, 3,600 minus 2025, yep, square rooted is 39.69 feet. 39.69 feet. If he is standing at 39.69 feet, that's the farthest back he can go with a 60-foot rope. If he goes closer, he uses less rope. That's all he has is 62 feet with the extra end pieces, right? The 1 and the 1. So the farthest back he can go is 39.69. The question is the ratio 45 over 39.69, can he stand at some location so that the rope is not steeper than? Is this less than 5/4? If that's less than 5/4, we have a winner. So I say we turn these both into decimals and look at them. 1.25, that one's easy, 1 1/4. This one, if I take 45 divided by 39.69, I get 1.13. Since this is less than that, the answer is yes, he can stand in some location so that the slope is less than 5/4. So yes, comma, 62 feet of rope will work. Maybe something like that for an answer. There is an alternate way to do this problem, and that would be, see if I can think of it here. You could figure out what would the distance here have to be, like we did on the previous problem, so that you get exactly 5/4, and then take that number and see if the 60-foot rope will work, and you'll find out that way it also works. But for time, I'm going to just stop right here, and then please take good notes on this and ask good questions when you get your opportunity. Thanks for listening.